everyone. In today's video, we are going to be working on exponential and logarithmic equations. Exponential equations are equations that have an x in the exponent, so maybe like 2 to the x plus 5 equals 7 to the x squared plus 6. And then we'll look at logarithmic equations, and those are equations that have logs in them. So we're going to have to use the properties of exponents and logarithms to help us solve the equations. So we are going to start with exponential equations. So one thing to do, and if you look at example one thing that we can try when we're solving exponential equations is to try to get the same base. So we always want to see if we can try to get the same base. So try to rewrite the equation with the same base. So that means in this example where I have 25 to the 3x equals 125 to the x plus 2, I want to try to write those so that this number and this number are the same. Well, right now 25 and 125 are not the same, but if I think about 25, I realize that 25 is the same as 5 to the second power, and then 125 is the same as 5 to the third power. So I'm going to replace the 25 with 5 squared. Bring down that 3x. I'm going to replace the 125 with 5 cubed. And so now my equations have the same base. Next, now that I have the same base, I'm going to simplify it a little bit with my property of exponents that say if you have a power to a power, you can multiply those exponents. So this would be 5 to the 6x equals 5. Now I'm going to distribute this 3 to the x and the 2. So 5 to the 3x plus 6. And now I really have the same base. And that's helpful because I have an equation. The left side is equal to the right side. So if the left side is 5 to the something and the right side is 5 to the something, and it's an equation, then the 6x must be equal to the 3x plus 6 in order for this equation to be true. And this is called the property of equality for equations. So if you have the same bases raised to different exponents, you can set the exponents equal to each other. So I have that going on here. I'm going to solve for x, subtract 3x on both sides. I get 3x equals 6, divide both sides by 3, and x is going to be 2. I'll try it again in example B. 0.001 equals 10 to the 6x. I always want to try to write this with the same base. 10, I'm going to leave that alone, so I'm going to leave it as 10 to the 6x. 0.001 is the same as 10 to the 1, 2, 3 to the negative third power. Or 1 over, that's 1/1000th, which is 1 over 10 cubed, so 10 to the negative third. So now I have 10 to the negative third equals 10 to the 6x. The bases are the same, so I can set the exponents equal to each other. Negative 3 equals 6x. Divide both sides by 6. Negative 1/2 is equal to x. Then here is one more extra example you can add in your notes if you want. I've got 1/2 and 4. Now I know that 4 is the same as 2 squared to the 3x. And 1/2, if I want to try to write it with the base of 2, that's 2 to the negative 1 to the x plus 7. So then if I apply properties of exponents, power to a power, you multiply those two. 2 to the negative x minus 7 equals 2 to the 6x. Now I have the same base. Yay, same base. So I can say negative x minus 7 equals 6x and solve for x. So negative 7 equals 7x, and I get that x equals negative 1. Now in example 2, I have another exponential equation, 5 to the x equals 12, but this time I cannot write bases 5 and 12 as the same base. So the same base is not an option for these two, and I can't apply what I did in the one below. So I can't get the same base. So in the past, we have tried changing this to log form. So if I change it to log form, I would have log base 5 of 12 equals x. And then I could grab my calculator, find out what log base 5 of 12 is, and I'll solve for x. And we get that x is approximately 1.544 if I round to 3 decimal places, which is great if I'm allowed to round. If I'm not allowed to round, then I can use something called the change of base formula, which we worked on last lesson. Change of base says that if I know that x is equal to log base 5 of 12, then x is equal to the log base 10 of 12 divided by the log base 10 of 5. Or if instead I wanted to use the natural log, I could say it's equal to the natural log of 12 over the natural log of 5. But where did this change of base formula come from? It comes from this property. Where is that property at? It's somewhere in this property right here. It says that if I have an equation, which we use an x equals y equation, I can do whatever I want as long as I do the same thing to both sides. So I'm going to have an equation, and instead of changing it to log form, I'm going to take the log of both sides. And that's where we'll have our change of base come in. So we're going to stick with that idea. So my original equation was 5 to the x equals 12. I'm going to use this property saying that if I have an equation, I can do whatever I want. I'm going to take the log of both sides. So I'm going to say the log of 5x, or sorry, 5 to the x equals the log of 12. And I'll apply my log properties after that. So if I take the log of both sides, now I can apply the log property that says this exponent can come into the front, and I have x times the log of 5 equals the log of 12. And then to get the x by itself, I could divide both sides by the log of 5. So then x is equal to the log of 12 divided by the log of 5. Now, if I look at, and then if I type that into a calculator, I'll get the same decimal I did before. So if you look, log of 12 over log of 5, 2 different ways to get this answer. And this is where the change of base came from. And if you're like, Ms. Honeycutt, why are you doing this simple problem 3 different ways? It's because these equations are going to get a little more difficult. So we could have something like this, example 3. I have another exponential equation. I cannot try to get the bases to be the same. So instead, I'm going to take the log of both sides. I'm going to apply that property. So I'm going to say that I have the log of 2 to the 3x is equal to the log of 7 to the x plus 1. And since I've taken the log of both sides, now I can apply log properties that's going to help me get the x out of the exponent. So the 3x is going to move to the front, the x plus 1 is going to move to the front. So now I have 3x times the log of 2 equals x plus 1 times the log of 7. Now this x plus 1, I need to make sure I put it in parentheses because that whole thing is being multiplied by the log. Now I've got an x here, I've got an x there. I need to get all my x's on one side. So the first thing I'm going to do, I'm going to distribute this log of 7. So now the left side is 3x log of 2 equals x times the log of 7 plus 1 times log of 7 is log of 7. And I see that there is an x in this term and an x in that term. So I'm going to get all my x's to one side. So I'll subtract the x log 7 on both sides. So 3x log of 2 minus x log 7 equals the log of 7. Now I can't subtract the 2 and the 7. I can't if I were to try to condense these two logs into one, then I would still end up with these x's back in the exponent's place. So instead, I'm going to factor out an x. So if I factor out an x, then I have 3 log of 2 minus the log of 7 equals log of 7. And now I just have 1x. It's being multiplied by all of this, so I'm going to divide both sides by that. So x is equal to the log of 7 divided by 3 log 2 minus log 7. So that would be my answer. And I could then find my decimal approximation for that. Now, if you want to do another one of those, if you flip to page 314 and look at number 23, you'll see the equation 4 plus 5 to the 6 minus x equals 15. So here I have a 4, I have a 15, and I have one exponential expression. Before you take the log of both sides, go ahead and combine the 4 with the 15 so that you have 5 to the 6 minus x equals 11. Now I can't get the bases to be the same, but I can take the log of both sides. So log of 5 to the 6 minus x equals the log of 11. Bring that 6 minus x in front. 6 minus x times the log of 5 equals the log of 11. So then, let's see, got that x tied up in the parentheses. I could distribute. Now, this is not the only way to solve the problem, but this is definitely one. 6 log of 5 minus x log of 5 equals log of 11. I noticed that the term with the x is right here, so I'm going to subtract 6 log 5 on both sides. Negative x log 5 equals log of 11 minus 6 log 5. And then if I divide both sides by negative log 5, x will be log of 11 minus 6 times the log of 5, all divided by negative log of 5. So this would be the unsimplified version. Then you can type that in to a calculator, come up with a decimal approximation. Now let's talk about logarithmic equations. Logarithmic equations are equations that have one or more logarithms of a variable expression. So that means you have a log base 3 of an x, log base 3 of an 8. We have a couple of methods we can use to solve these types of problems. So let's look at example 5. One thing I notice on example 5, I have log base 5 equals log base 5. Well, this is an equation. This side is the same as the other. So this log property says that if I have log with the same base on both sides, then I can just set the arguments equal to each other. So in example 5, I have log base 5 of x squared minus 45 equals log base 5 of 4x. Since those logs are the same, then I can just solve the equation x squared minus 45 equals 4x. because these logs are the same. Now you can only do it if you have log equals log. If you had another expression like log plus log equals log, then you would need to combine these two logs together before doing this. But anyway, I see that in the blue I have a quadratic equation, so I'm going to try to factor it. Set it equal to 0 first. X squared minus 4x minus 45 equals 0. Factor. I get an x and an x. Minus 9 plus 5. So I get that x equals positive 9 and x equals negative 5. And it looks like I have two answers. However, remember that you can only take a log of a positive number. So, a number. So I have to make sure that whatever I'm taking the log of is not 0 and not negative. So I'm going to substitute the 9 in right here. 9 squared minus 45 is positive, and then 9 times 4 is also positive. It's positive, so x equals 9 is a solution. Then if I try substituting in negative 5, negative 5 squared is 25. 25 minus 45 is negative. So x equals negative 5 is extraneous. You could have one solution, multiple solutions, or no solutions. Then if you look at, I thought we had an example B somewhere. Here's example B. Natural logs will work the same way. So I see natural logs, they both have the same base. So I can set up negative 4x minus 1 equals 4x squared and then solve. There's a couple extras you might want to look at, like 37 on page 314. Take a look at that one. So 37 is one that I was talking about where they're all log base 6s, but on the left I have one log and on the right I've got two logs. So I need to find a way to combine these two together. I'm going to combine these two with log properties. I'll use that product property that says if I've got two logs being added together, I can write it as one log of the product of those two. So of 2x minus 3 times x plus 1. Log base 6 of x squared minus 2x. So let me simplify on the right. Log base 6, if I multiply this out, I'll have 2x squared plus 2x minus 3x. So minus x minus 3 equals log base 6 of x squared minus 2x. So now I'll have the equation x squared minus 2x equals 2x squared minus x minus 3. It's quadratic, so I'm going to set it equal to 0. Subtract the x squared, I get x squared. Add 2x, I'll have plus x minus 3 equals 0. Then I'll try to solve. So then I go to factor this, and I think, okay, are there numbers? Will this factor? Please, please factor. 3 and 1 are not going to combine to be 1. Oh, no, it doesn't factor. So what can I do? I can apply the quadratic formula. So I'm going to apply it on my calculator. So I know that x equals negative b, which is 1, plus or minus, so I'm going to start with the plus. X equals negative b plus or minus radical b squared, so 1 squared, minus 4 times 1, 4a, times c, negative 3, all over 2 times a, which is 1. So I'm getting that x is approximately 1.303. 1.303. And then remember, quadratic formula says x equals negative b plus or minus. Change that plus to a minus. So then x is approximately negative 2.303. And then I have to figure out, are either one of these extraneous? So if I substitute in 1.303 squared, I'm going to substitute 1.303 in for these x's, because I have to make sure that I'm not going to take the log base 6 of a negative number. So I'm going to take x squared minus 2x. The graph, don't pay attention to the graph. So x squared minus 2x, I'm going to plug in 1.303. 1.303 squared minus 2 times 1.303. That's negative. This number would be negative, and we can't take a log of a negative number. So that means 1.303 is extraneous. Negative 2.303, so let's substitute in negative 2.303. And right here, negative 2.303, that's positive, so this part would be positive. Now we have to check the 2 times negative 2. We have to check this one, and we have to check the other one as well. Ooh, and if I look right away, negative 2.303 plus 1 is also going to be negative, so that one is also extraneous. Which means this one has no solution. The other thing you have to do is you'll have to do what example 6 says. It says solve the equation by graphing. So you're going to graph two equations. You're going to graph y equals the left side. So y equals 3 times 2 to the, now you have to use parentheses here, x plus 2 to keep that in the exponent, minus 1. So I'm graphing the left side. Now I'm going to graph the right side, y equals 3 minus x. I'm going to figure out where they intersect. These intersect right here. And since the equation only has x's in it, my x, round to the nearest thousandth, that's 3 decimal places, is approximately negative 1.205. Now, if they ask you for more decimal places, you can zoom in on Desmos, and it will give you more decimal places eventually. See, negative 1.2051. All right, so in summary, if you're trying to solve an exponential equation, the first thing that you want to try to do is try to write it so that it has the same base first, and then set the exponents equal to each other. If you can't rewrite it so that they have the same bases, then you're going to take the log of both sides. Log equations. If you can get it in the form log equals log, that's what you want to try to do, then you can set the arguments or set whatever you're taking the logs of equal to each other. If you have like log plus or minus log equals log, you're going to need to apply log properties first. And then do this. If you have a scenario where you have log equals a number, that you might be able to try by just changing to exponential form. So make sure you have this guy down as some shorthand. Good luck on this assignment. We will work on this and practice more in class to make sure that you are well prepared for this. Hope you guys have a great day, and I'll see you soon.